Talk. Let me introduce you Professor Sandra Augusta Santos from the Department of Applied Mathematics in the University of Campinas. So she is going to talk about us on the solution of nonlinear least square problems, recent contributions and perspectives. So, you may proceed.
Thank you very much for the introduction. Good morning, you all. I'd like to acknowledge my institution, State University of Campinas, and also the Brazilian founding agencies that gave support to our research. Today I'll talk to you about solution of nonlinear least squares problems, and this work was developed with several colleagues, and I will acknowledge them along my presentation. So this is the outline. I will start with some motivation, and then give you the definition of the problem and some notation, a brief timeline with authors that have addressed this problem, and our 4 recent contributions along these 4 subjects. Then, final remarks and some references conclude my talk. So for the sake of motivation, I will talk a little bit about data assimilation. This is an applied context in which nonlinear least squares appears very much. Basically, we have observed data and a model which is built based on initial state and parameters that have to be adjusted. So the idea here is to minimize the gap between the observed data and the model. And the nonlinear least squares model is used in this context. For example, in meteorology, there are 100 million observations and 10 million variables. So the problems are huge and challenging. A very, very simple scheme for give you an idea of this data simulation context is given here. Let us say we have these observations, and we build a model in this sense. This model is basically built by minimizing the quadratic error between the observations and the model. And the idea of the quadratic error is to preserve smoothness in case the model has smoothness. And the idea here is to use the model to make some prediction. Okay, so this is the notation that we are going to use. We have a vector-valued function, usually with much more components than variables, and this is called our residual function. And we assemble a scalar function by summing the squares of the components of this residual function and consider the minimization of this scalar. This is the nonlinear least squares problem that I'm going to address as NLS. Because of the smoothness of the residual function, the problem has a very nice structure. Here you see the gradient of this function, in which we use the Jacobian matrix denoted by J of f, and also the Hessian matrix that has this very nice structure. This separable structure in which we have first-order derivatives and the second-order derivatives here. Okay, in case one has a point in which the residual function is 0, notice that at the Hessian, this term is going to vanish at the solution. And then the Hessian just has the first-order derivatives, the component of that. Also, in case the Jacobian is full rank, then because of the second-order sufficient conditions, this x star is going to minimize globally the function that defines our unconstrained problem. So this is the easy problem, the zero residual and full rank case. Okay, as is usual in nonlinear programming, a solution to a problem is built iteratively. So we build a sequence of approximations aiming to converge at a solution of the problem. And one of our nice tools for that, and fast, is Newton's method, in which our sequence is built by means of adjusting and updating the sequence, solving this linear system in which the matrix of the coefficients is the Hessian matrix. Okay, but as I told you, remember that this is the structure of the Hessian, and in case we have a zero residual problem, then as the sequence converges to the solution, so as xk gets close to x star, this term is going to vanish. So approximating and do not considering this term may be a good idea. And in this case, we have the so-called Gauss-Newton system, in which just the first order part of the Hessian is considered for the matrix of coefficients. Naturally, for this system to be well defined, the Jacobian must have full rank. And also, in this situation of zero residual, and also maybe if the Hessian is zero, because the problem is affine, these are two circumstances in which Gauss-Newton will behave like Newton and we will have a fast quadratic convergence. But unfortunately, the assumption of full rank is quite strong, and sometimes we do not have that. So we have to dump the spectrum of J transpose J by means of a scalar matrix. And this parameter that performs this dumping, this shifting in the eigenvalues, is called the Levenberg-Marquardt parameter. And controlling this parameter is indeed an issue, because if it is too small, maybe we are not controlling the conditioning of the system. And in case it is too large, then the direction might be too much oriented towards the steepest descent direction, and the method is going to be slow. So this is really a subject of research. And also, for weakening this full rank assumption of the Jacobian, but also addressing the problem with zero residual, the error-bound conditions are good tools. For example, if we take our solution set as the set of points in which we have zero residual, then we say that the norm of the residual provides an error bound for the set of equations if there exists a constant such that this relationship holds. Notice that this constant is in charge of adjusting the units, because we have to combine a unit in the domain and a unit in the range space. Okay, now that we have seen some of the terminology, I can provide you a brief timeline on names of authors and works along time. So no doubt, the seminal works of Levenberg and Marquardt are the most known research in this area. But one should also acknowledge the work of Morrison, that is sometimes forgotten, but he also proposed the same strategy as Levenberg and Marquardt. Here in this list, we can identify very important names for our community in smooth optimization, like Mike Powell, John Dennis, Georges Moret, Philippe Tuan, and so on. In this research, most of the efforts are concentrated in derivative-free strategies and also structured quasi-Newton methods. And they were developed in the last century. Now, concerning the 2000s, the interest moved more for problems with rank-deficient Jacobians. And in this research, huge problems also started to be addressed, as well as the worst-case analysis that became fashionable. So this goes mostly to 2010, and in the last 10 years, the interest on problems which the Jacobians are rank-deficient continues. Also problems with not only unconstrained nonlinear least squares, but also problems with simple bounds, and the complexity analysis as well as ill-posed problems keep interest of the community. And enlarging this list and giving you some details on specific problems, I will mention our recent contributions, and I will start with this work in which we proposed a spectral correction for the Gauss-Newton method. This work was developed with Douglas Gonçalves, and our idea was to do the following. Let us recall here the expression for the Hessian, and we have our sequence of approximations for the solution, and we are going to call this part of the Hessian as the matrix Sk. And in this work, we have approximated our second-order derivatives by scalar matrices concerning each of the residual functions. And this scalar has the spectral philosophy of Barzilai, Boring, and Haidam, in which these vectors S and Y are defined in this way. As a result, our matrix Sk is indeed a scalar matrix in which this scalar alpha may be written with this expression or even in matrix form in this way. It's important to mention that this scalar is sign-free, is not non-negative as the Levenberg-Marquardt parameter, and it carries second-order information from the Hessians, and it provides a second-order correction for the Gauss-Newton method. So the algorithm is very simple. I will use this short notation for the residual function and the Jacobian at the iterates. We start at an initial point and with an initial spectral parameter, and the loop, mainly we have to solve the system, update our approximation, and update the spectral correction, and so on. So this is a local algorithm because we are taking the full direction as the iterations goes on. So in case our residual functions are quadratic, then we have a very nice structure because our parameter is simply a Rayleigh quotient, so that it is between the smallest and the largest eigenvalue of matrix Sk. And we'll denote these eigenvalues using sigma, and by lambda min and lambda max k, we'll denote the smallest and the largest eigenvalues of the Jacobian transpose the Jacobian. And use the same notation concerning this x star, that's going to be a stationary point of the problem, and we are going to use the star to denote the extremes eigenvalues for S and for J star transpose J star. Okay, so to give you an idea of our result, I will start with the classical analysis of convergence of Gauss-Newton as presented and proved in Dennis and Schnabel's book. So let us say that our function, our objective function of the NLS problem is twice continuously differentiable, and the Jacobian is Lipschitz continuous and bounded. And we assume that we have a stationary point, x star, for which this relation holds. Notice that this scalar sigma must be bounded by the smallest eigenvalue of J star transpose J star. And this relation should hold as well. Having all these hypotheses, then we have a neighborhood in which we start the Gauss-Newton method. It is well defined, converges to x star, and obeys this relationship here. Notice that from this relation, we can see that this scalar sigma plays a role of combining the nonlinearity of the problem and the size of the residue. In case the problem has zero residue, f star is 0, and then sigma is 0 also. In this case, we drop this term, and we have quadratic convergence as the relationship with the errors carries this square here. And also it's important to see that the role performed by the Jacobian is important because it must bind, this smallest eigenvalue must be an upper bound for sigma. So not only the Jacobian must have full rank, because it must be greater, strictly greater than 0, but this relation must hold so that we have the necessary contraction here for convergence. So to see even better this relationship and the importance that the Jacobian carries in this case, we have this relationship concerning that term that appears in the condition of the theorem, and when the residual functions are quadratic, indeed this relationship holds as equality, so that we can interpret the scalar as the to norm of matrix S star. And this implies that the spectral radius of this matrix satisfies this relationship here. And for our analysis, we have assumed that these two relations hold. In the first one, in A1, we are assuming that the smallest eigenvalue of S must be lower bounded by minus lambda star mean. And in the second assumption, the length of the interval that contains the spectrum of S star must satisfy this bound with this sum in this case. So it's nice to see that in case our matrix S star is not positive definite, using these two assumptions, we obtain this relationship concerning the spectral radius. But if S star is positive definite, together with this condition, we reach our assumptions. So in this circumstance, we see that our assumptions are slightly weaker than the traditional, the classical hypothesis of Gauss-Newton. So these are the results that we have obtained. The first one concerns the well-definiteness of our algorithm. So it says that it's always possible to compute the direction because our matrix, the inverse of the matrices are bounded. And we have the linear convergence of our scheme. If we recall the constant from Gauss-Newton, we see that this is kind of more complicated, but it's interesting to mention that in this, whenever Gauss-Newton converges, our constant that provides the linear convergence is slightly better. So to give you an idea on the performance, I provide here an illustrative example, a very geometrical one, is a problem with non-zero residue. We are accommodating these three residual functions, and in this case, this matrix is singular, so that Gauss-Newton really diverges. Here we have the behavior of the iterates. They started from here. Here we have a zoom. This is the initial point, because as the iterates they try to reach the optimal solution, the matrix become more and more ill-conditioned. On the other hand, the spectral corrected solution, they converge in 9 iterations just with optimality criterion of 10 to minus 8 for the norm of the gradient. Okay, so summarizing this contribution, we have devised a simple spectral correction for the Gauss-Newton model, which is locally convergent. And it was interesting to see that we could ensure convergence in case the classical Gauss-Newton could not converge. Basically, we need a sufficiently bound spectrum for S star, and even in the circumstances that Gauss-Newton is not convergent, maybe if we have this matrix singular, as long as the spectrum of S star satisfies this relationship, we can ensure the convergence. And as I have mentioned, in case Gauss-Newton converges, the linear convergence of our scheme is slightly better. Okay, so the second contribution, this was developed together with Elisabeth Caras and Benares Weiter. And here we are addressing the Levenberg-Marquardt parameter, and we have algebraic rules for building it. So we are assuming that our function, our residual function is of class C1, and we have Lipschitz continuous Jacobian. And the idea here, I recall the Levenberg-Marquardt sequence, and we would like to select this parameter mu k, such that this direction is as large as possible, and we can take the step length 1 when we are ensuring if we have sufficient decrease. And we use the Arminian line search for detecting this decrease. So briefly, in these slides, I have removed the iterate k, just not to burden the notation, but we are at a certain iterate. Here we have the classical linearized error, and I have recalled the expression for the Levenberg-Marquardt step. So we have devised two bounds, two distinct bounds for this step based on problem information. Here, PR is the notation for the projection on the range space of the Jacobian. So based on these two bounds, we have also devised a bound for the prospective value of the objective function. And the idea here is to impose conditions based on these bounds, to impose conditions on mu so that we have non-positive term. This term is surely non-positive. And indeed, we obtained that. We obtained this lower bound for me based on this condition, and also this other bound based on this condition here. And every time we take mu greater than one of these two values, for sure this inequality is obtained. And here, because we will have descent, this is non-positive also, so we are decreasing the objective value. So whenever we are not stationary and we take mu larger than this value that we are going to call mu minus, then the Levenberg-Marquardt step is a distant direction. It's going to be accepted with step size 1, and then we also have these two values, mu plus and mu j, in which we are having the upper bound for selecting mu. So the algorithm, briefly, I will mention that we initialize and we choose our Levenberg-Marquardt parameter among these two values, mu minus and mu plus. Indeed, we set it as the minimum between mu j and mu plus that I defined in the previous slide, compute the solution, perform the line search, and then update our approximation for the Lipschitz constant of the Lagrangian, of the Jacobian. Because many times we don't have access to this constant, but we can approximate it dynamically along the algorithm. And for this approximation, for this updating, we use ideas from trust region. Okay, it was not difficult to see due to the way we have developed our parameter, that the algorithm is well defined. The line search is going to be performed in finite time, and it's globally convergent in the sense that we can start from any initial point and obtain a stationary point. And also, concerning the problem with zero residual and under an error-bound condition, we obtain quadratic local convergence. So to assess the performance of these ideas, we have tested the algorithm for 53 feasibility problems from this collection. We implemented it using MATLAB and used a routine from MATLAB, LSQ nonlinear, as the benchmark. Our problems have dimensions varying between these two values, and we have used two strategies for computing the step, either the Cholesky factorization of this matrix in this sense, or the QR factorization of this augmented system like this. So CH and QR are our strategy with these two choices for computing the step. LM is the Levenberg-Marquardt from MATLAB, and we also addressed and encoded the algorithm of Fan and Pang, which uses the Cholesky factorization and has a dynamic way of updating the Levenberg-Marquardt parameter. So here I show you the performance concerning the evolution along the iterations for the objective function value in log scale. So blue and green are our colors, and they correspond to these curves that coincide, so we see that we reach the quadratic convergence faster in both circumstances, and these two problems are quite typical. So here we are addressing just the evolution for two particular problems. But for having the whole idea of the performance for all the problems, I present here the performance profiles. For number of iterations, for number of function evaluations, and for CPU time. For those who are not familiar with this kind of graph, they are cumulative distribution graphs. And roughly speaking, the higher, the better. Here on the left, we can see efficiency. So the higher, the most efficient. And here we see robustness. So the higher, the most robust. For these two measures, the curves goes quite together. So it's hard to say who is the winner. In terms of CPU, we see that Cholesky factorization is faster than QR factorization as expected. But concerning the robustness, I should mention that from the 53 problems, our strategy managed to solve 50. Levenberg-Marquardt, our strategy managed to solve 51, Levenberg-Marquardt 50, and Fan and Pang 49. So everything is quite close in this case. So just summarizing, our algebraic rules were devised with the idea of having a large direction and accepting it with step length 1. They were developed using the Lipschitz constant for the Jacobian, but in case this Lipschitz constant is not available, then we can update it dynamically, and that was the main idea. Under an error-bound condition, we obtained the quadratic convergent, and our numerical results were encouraging. Okay, so let's go to the third contribution. Just to motivate our contribution, let me just summarize the solvers for nonlinear least squares. And we start with the Newton's method, as we have already seen. We are using in this method, we use the whole Hessian, so it might become expensive due to the second order derivatives that have to be computed. In case we drop this part, we have Gauss-Newton. That is nice, very good indeed for zero residual problems, but maybe not that well for non-zero residual ones. The idea of Levenberg-Marquardt was to shift the spectrum of J transpose J with this non-negative parameter that is very useful when we have rank deficient problems. Also, the whole Hessian might be approximated in a quasi-Newton fashion, and then the structure of the problem is just ignored. Or also, we could use the quasi-Newton idea to update just the second order part of the part that contains the second order derivatives. And in this, we are taking care of the structure of the problem, but due to memory requirements, this might become expensive. And also, we have this sign-free spectral correction for the Gauss-Newton, as I have presented to you, our first contribution. And another possibility would be to approximate this matrix by a diagonal one, and this matrix by a diagonal one also separatedly, and taking into consideration the structure. So this we call structure diagonal Hessian. We have a complete approximation with the structure, and this is our approach. This work has been developed together with Hassan Mohammad from Nigeria. And the algorithm is called SDAJM from the initials of this title here. So the idea is to approximate our current Hessian by means of a diagonal matrix. In the very beginning, it is just the identity, but as the iterations go on, we have information so that we can build this diagonal matrix component-wise, resting upon these vectors y hat and y bar. These vectors carry spectral and secant information correspondingly to the terms they are approximating. I recall that this approximates G transpose J, and this approximates the matrix S. So we have devised safeguards for these components, because we have to be sure that we have a positive definite matrix, so all the components must be strictly positive. And in case this denominator here is 0, we simply set it as 1, so it is a kind of restart. Okay, the algorithm is quite simple. The main parts are the computation of the correction for the iterates, and we have to solve this diagonal linear system, which can be solved in order of number of variables effort. And we have a non-monotone line search due to the spectral ideas. We have used the Zhang and Hager line search that uses these elements here, and safeguard a quadratic interpolation for computing the step length based on the Dennis and Schnabel's book algorithm. So to obtain the evaluation complexity analysis result, these are the assumptions. They are quite standard. Boundedness of the level set of the problem, twice continuously differentiability of the nonlinear least squares function, and uniform continuity of the gradient. This is slightly weaker than assuming that the Jacobian is Lipschitz. So we proved that our directions are of descent, and they are gradient related. And with this hypothesis, and based on this lemma, we show that our algorithm is well defined, in the sense that the line search can be performed in finite time. And this is the evaluation complexity result, which says that we can compute an epsilon stationary point in order of epsilon to minus 2 iterations, or function evaluations, basically. So I recall that this constant rho really depends only on algorithmic parameters, and constants that depend on the problem, the Lipschitz constant and the initial value. So these do not vary along the iterations. That's why we have an order of epsilon effort here in terms of function evaluations. So to assess the performance of SGHAM, we have solved 40 structured problems from the literature, and they are divided, and they have 0 small or large residuals. Our matrix vector products that are necessary for the iterates, they are computed in a matrix-free way, so we do not assemble the Jacobian, we just have the effect of the transpose times a vector. And we have compared our algorithm against 4 benchmarks. The first 2 are more recent from the literature. This one was developed for unconstrained minimization and uses a diagonal approximations as ours. And the second one uses the conjugate gradient method for nonlinear least squares exploiting the structure of the Hessian. And we also compared with these 2 classical benchmarks, the globalized Barzilai-Emboring from Braidan and the conjugate gradient of Fletcher-Reeves. So we divide our comparison first with these 2 and then with these 2. So in the first comparison, here are the performance profiles. Besides iterations, function evaluations, and CPU time, we are also addressing the matrix vector products performed per iteration. And here we see that we are really much more robust than the competitors and more efficient for these 2 measures. But for matrix vector products, we are not as efficient as this algorithm here. But the reason for that is that we have a structured way of computing our iterates. For CPU time, there is a kind of tie. When we consider the other 2 competitors, then we also managed to be slightly more robust, solving most of the problems. In terms of iterations, kind of tying this measure, and also in this one, we lose in terms of matrix vector products, and concerning CPU time, that's the performance. So we are basically more robust than the competitors, but not as efficient in some of the measures. Another interesting way of analyzing the results was to checking the matrix vector products per iteration when we are concerning the algorithms that really perform matrix vector products. And we see that the median of our algorithm is always 3 and never above 4, whereas for the competitors, these distributions are much more spread. So all in all, in SGHAM, we have a matrix-free strategy that uses these matrix vector products without assembling the Jacobian. The solution of the linear system that has to be performed in each iteration can be done in just order of number of variables operations. And our algorithm does not care if the problem has 0, small, or large residual. And we have a worst case complexity result that says that we can obtain an epsilon stationary point with this order of function evaluations. Now, the last but not the least contribution is an analysis of the local convergence of Levenberg-Marquardt without the assumption of 0 residual. And this was developed together with Roger Belling and Douglas Gonçalves. So here is the problem, our problem of interest, and we are not assuming 0 residual. So the solution set now is going to be the set of points for which we have stationarity for this problem. We are assuming that we have stationary points, and we are considering a neighborhood of a certain stationary, a specific x star from this set. And we are using the bar for addressing any point that is stationary and it's close enough to x star such that this condition here holds. So our basic assumptions are, again, Lipschitz continuity, but in this case, just local Lipschitz continuity in this neighborhood. And we also assume that we have this error-bound condition. Notice that now we are using the norm of the gradient of the function as the error bound, not the norm of the residual function, because we are not assuming 0 residual. So what really goes to 0 is the gradient. And we assume this lower bound, this error bound in a neighborhood, in our neighborhood of analysis. And I recall that omega is our constant in this case. Okay. So basically, we have the classical linearization error for the residual function, and we just need it in a neighborhood in our neighborhood of interest. And because of this neighborhood, we have the boundedness of the norm of the Jacobian and the norm of the residual, so that both are Lipschitz also. And we use this incomplete linearization for the gradient, in which we are not considering the second-order derivatives of the part of the Hessian. That's why we called it incomplete. And that's why we do not have only this squared term, but also this remaining one that we have to take care. And finally, because of the error-bound condition and using this Lipschitz continuity, we have this relationship concerning the norm of the gradients along the analysis. So to take care of this part that remains in the bound, we had to impose conditions that will tell us how to manage on that. And these are the conditions. Basically, for a point in a neighborhood of interest and for all stationary points sufficiently close to x star, we are assuming either that we have this condition or this one or this one. They basically are different because of the power that appears here in the right-hand side. Naturally, if the problem had 0 residual, these conditions hold with 0 for the constant, but we are really addressing problems with non-zero residual, and that's why we need to divide our analysis depending on the conditions. So I recall here the Levenberg-Marquardt local iteration, so we are taking the full direction, no step length control. And our first result says that under the Lipschitz continuity of the Jacobian, and if we assume that the rank of the Jacobian is constant, equals to p, in all points in this neighborhood, then we manage to have a bound on the direction that has this distance appears here. Now, if the rank is not constant and is just greater or equal to 1, but can diminish as we are approaching the solution, then the analysis will really depend on the conditions, 3, 2, 4, and 5. And in the constant rank case, no. But in the diminishing rank, for example, under A3, we need to be sure that our Levenberg-Marquardt parameter is bounded in this sense for this bound to occur. For under A4, mu k must be chosen in this way, and under A5 in this way, as the norm of the gradient at the current iterate. So depending on the choice and on the assumption, then we have this inequality. And these are going to be just summarized in this table. In the constant rank, the mu k may be just taken as the norm of the gradient at the current iterate, and in the diminishing rank case, then depends on the assumption. We need to make distinct choices for the Levenberg-Marquardt parameter. It's important just to clarify this hypothesis here. This is important because it implies that we have a uniform lower bound for the meaningful part of the spectral decomposition of JK transpose JK, so that we can really safely bound it from below. Okay, so because of our way of analyzing, and because we don't have zero residual, there are some terms that have to be addressed, and this auxiliary result turned to be really important in the analysis. Here appear the terms that are going to demand assumptions 3, 4, and 5. And depending on that, from this lemma and under each one of the assumptions, we managed to prove that we are having the necessary contraction for convergence, and then we can discuss the neighborhood in which we have convergence quadratic, superlinear, or linear, depending on the case. So basically, if we are under constant rank and have assumption 3, then we manage to obtain not only the contraction, but we manage to prove convergence with linear rate. With A4, we have the contraction and superlinear convergence of this sequence to 0. And under A5, and even in constant rank, the contraction and quadratic convergence. Now, when we talk about diminishing rank, then the analysis is a little bit more challenging, and depending not only on the assumption that we are doing, in this case we start with A5, but also on the choice of the Levenberg parameter. So with this choice, we managed to obtain this bound. Using lemma 4, we have the contraction, and then we have quadratic convergence. With A4 and under this choice for mu, we have these bounds. Using lemma 4, we have the contraction, and the convergence is going to be superlinear. And finally, under A3, we need to choose the Levenberg-Marquardt parameter among these two values to obtain the bound for the size of the direction, so that we are sure that we have the contraction, and then the convergence is going to be linear. So to illustrate these ideas, geometric and simple examples where we can see the details. For example, here, this is the residual function. For example, the points in which the first residual function is 0 is this blue one, and the second is this orange one, so that the solution, the compromise points, are this one that are in black in this level set plot, and here we have the surface graph of the nonlinear square function. Here is the Jacobian, and in this problem, the rank of the Jacobian is constant, and these are our non-isolated minimizers. Okay, so in this case, our set of stationary points can be written algebraically. This is the expression for the distance. We have considered this point as the x star with a neighborhood with this radius, and these conditions hold with these values for the for the constants. And we could follow the quadratic convergence starting with this point and using μk as recommended by the analysis. And we reach this stopping condition with quadratic convergence. In the second example, we have also two residual functions, but now the rank of the Jacobian diminishes as we approach the stationary points. There is a global solution. Here in the plot we can see it. And there are also a set of minimizers where the gradient is 0, is this straight line in the level set plot. And we are addressing the analysis concentrated on this point here. So we have the expression for the stationary points, the distance. This is the point, the size of the neighborhood. Again, A5 holds. These are the values of the constant. And we also had quadratic convergence. And in our third example, the rank is diminishing as well. These are the functions. We have a set of non-isolated stationary points. But in this case, neither A5 nor A4 hold, just A3. And because of that, even starting quite close to the solution, and we, in taking a constant value for μk as recommended, we just obtain linear convergence. So all in all, in this analysis, we have considered the nonlinearly squared problems with non-zero residue and used a narrow bound condition upon the norm of the gradient to perform the analysis. The parameter μk has to be chosen depending on the condition in case of the diminishing rank of the Jacobian. Because this can be approximated in this way, we see that the importance of the second order derivatives term of the Hessian is really crucial for fast convergence, in the sense that as the sequence approaches the solution set, this matrix has to vanish, otherwise we cannot have fast convergence. And we hope that our study shed some light on the Levenberg-Marquardt algorithms for non-zero residual problems. So basically, to finish my presentation, I'd like to mention that the importance of nonlinearly squared problems from the applied point of view is gigantic, but it is also important in our world of smooth optimization because we use it to start algorithms that demand feasible points. So this is also important to us. If we Google the expression nonlinearly squares in the Google Scholar, we can have 2 million results. So we see that this is really important for the research community. And I should also address Morrison because I think he deserves the same kind of credit of Levenberg and Marquardt. And basically recalling our contributions in this field, we had devised the correction for the Gauss-Newton method. It's based on spectral ideas, and also based on spectral ideas is our algorithm SDAJM. We have devised algebraic rules for computing the Levenberg-Marquardt parameter, and finally, we present a local convergence analysis for problems with non-zero residues. So I'll take advantage of our references here to acknowledge once more my co-authors. And here they are: Douglas Gonçalves from the Federal University of Santa Catarina in Brazil, Elizabeth Caras from Federal University of Paraná in Curitiba, Brazil, Benares Weiter from the Institute of Pure and Applied Math in Rio de Janeiro, Hassan Mohammad from Kano University, Bayero University in Nigeria, and Roger Belling, my co-author in this fourth work. He works at the Federal University of Santa Catarina in Blumenau. So thank you very much for your attention.
Okay, thank you very much for your presentation. So there is enough time for a couple of questions or comments. Yes, Rosa? The mic is coming.
Thank you very much for the nice talk. My question refers to the diagonal approximation, which you express in terms of two matrices. However, I've seen in the transparencies that you define the elements of the two matrices together, it seems to me, and you use them together also to solve a diagonal system. Could you tell us something about why it is necessary to distinguish between these two matrices? Where do you use the distinction between them?
Okay. Let me just go back there. Well, we made the distinction because as we have a sum here, it might be that one may be negative and the other positive, but the sum may be has to be positive. So that's why we control them separately, because we would like this term to take care of the second order derivatives. So here we have a kind of secant and spectral flavor. So in this case, despite this probably is going to be non-negative, this may be negative, but we have to be sure that we obtain this, the sum has to be positive. So if we safeguard them together, then we are just controlling the combination. So we are taking care of the secant structure that is behind the formulas. There are many details from the computation, but I can show you and we can discuss the details later on, because you know it's too many details to present. But I can explain you better if you want. Thank you.
Any more questions? So I think we may thanks again the speaker. Thank you very much.
Thank you.